All right, this video is going to cover part 2 of a 2-part video for the Algebra 1 Keystone Practice Exam 2017. This video is going to focus on Module 2. All the questions from Module 2 will be answered here. Feel free to fast forward to the question that you want to see. If you want to see a question from Module 1, go back to the previous video. All right, let's go ahead and take a look at our first question. The data below shows a pattern in the cost of an online data storage for different numbers of terabytes of data stored. We've got our table there, okay? If the pattern continues, all right, which equation describes the pattern in the cost of the online data storage? All right, if we're looking at finding an equation of something that has a constant rate, we are looking to use our formula y equals mx plus b. That is our slope-intercept form that is on our formula sheet. And in order to get our different pieces of it, we must identify first our slope, which is our change in y over our change in x. That's shown to you on the formula sheet as y2 minus y1 over x2 minus x1. What they're asking you to do is just simply identify this being y. All right, what is my change in y? Well, going from 240 up to 315, what is that change? And you can simply subtract the first one, the second one, 315, minus 240. All right, if in doing so, you will find that that is 75. All right, and just to be consistent, you can double check that that jump is the same going all the way down. All right, by subtracting 390 minus 315, and you see that it's 75 again, and so on. It's going down by 75 each time, meaning that my change in y is 75 over my change in x. X over here being the independent variable. All right, and here it's very easy to see. If you can't see it, all right, we got to go back in math a ways because we're only subtracting 1. All right, so this is going up by 1 every single time. That tells me that my slope is 75 over 1. 75 over 1 can be reduced to 75, giving me an equation that starts off with 75x. Now, from there, I can identify my answer right away, all right, because none of the other values have the correct slope. Now, they're not using y and x, they're using c and t, as we saw up here, all right, but it's still going to give us the same pattern recognition. If they had 2 that were 75, I'm going to continue this out to show you what you would need to do. All right, we don't know the b value. However, I can temporarily take any one of the values that they gave me, such as 3 and 240, and I can plug that in. 240 equals 75 times 3 plus b. And if I do 75 times 3, I get 225. And I could subtract that from each side to find out that 240 minus 225 is indeed 15, giving me my b value, my y-intercept, as 15 there. Okay, so either way we could do that. We could find our slope. You could also go back in your table if you wanted to. You could go back down to 2, then back down to 1, and then back down to 0 to see that 15 is the beginning amount of cost, the initial cost in this case. All right, let's go to our next question. All right, which graph represents a function? Remember, we've got relations here. Relationship is between two variables, in this case x and y, and a function is determined by a special type of relation. It is a relation in which every input has one and only one output. Inputs are represented by our x values, which on our graph are represented by vertical lines. Each one of these vertical lines represents an input. This input right here that I'm drawing represents when x equals 3. All right, the output is identified by where it touches my graph. All right, and we can identify the output as the y value, which there it looks like negative 1.3. All right, so as we're looking at this, we're looking at vertical lines that touch my graph, and every time they touch, I get an output. Now, if it's a function, each input, each vertical line can only have one output, which means I cannot draw a line where it would touch my graph twice. Notice in this first one, it did not touch it twice. But notice over here, I can draw a vertical line where it touches twice. All right, over here, I can draw a vertical line where it touches twice. Anytime you can draw a vertical line where it touches more than once, often twice here, an infinite number of times on this line right there. All of those mean that it's not a function. One thing you can do is called the vertical line test. I will use this little doohickey here, all right, where my gray line on the right of this box represents a vertical line, and I'm just going to slide that vertical line across my graph here, and I'm going to watch where it touches my black curve. And if it ever touches more than once at the same time, it's not a function. There, it never touched more than once. Coming across to this one over here. Right there we can see, just like I drew before, it's touching it twice all the way along there, so that fails. Down here, coming across, initially I'm okay, just 1 point, 1 point, up, but right there it fails. I hit 2 points. All right, right there it fails again. Right there it fails again. And then this one across here, anytime I hit any of these vertical lines that are going up, right there it fails, right there, boom, it fails. All right, so anytime you can draw a vertical line that touches more than once. One thing I do want to mention, however, is how I could change C here if they did one like this. If C were changed to look like this, where this is an open circle, all right, this is an open circle, this is an open circle, this is an open circle, open circle, open circle. If those were all open circles, that means that it would not actually touch twice because it would only touch the solid circle at that point. And that one then would be a function, just so you're aware. All right, let's go to the next one. Take a look at this one. The set of ordered pairs below is a relation, all right, telling us it's a relationship between x and y. That's good. All right, what is the range of the relation? Remember, we've got two things we look for when we're dealing with the values, all the possible values in a relation. And we have our domain and we have our range. Domain is the list of all possible x values in a relation, all right, and the range is a list of all possible y values in a relation. All right, I remember that because D comes before R alphabetically and X comes before Y alphabetically. So if I want the range, I want to look at all of the Y values here. I list the Y values from least to greatest and I do not repeat. All right, so now this is not an interval. It doesn't say that they're connected. It's merely a list of 4 points. And so my range is going to be a set of numbers starting with -4 as the lowest, then -1, then 2, then 5. I use these brackets to represent a set of numbers, all right, not an interval, and I come over here and I identify this as my range. This right here, all right, this one B, that would be my domain, all right, and then if we're looking at C, that is interval notation. It's saying it goes from -4 to 5, but we don't know that these points are connected with a line. All we know is only these 4 points are in there as a scatter plot. And then D would be if we did interval notation for our domain. So those are the different pieces they're trying to trap you with. All right, next question. A function of x is graphed on the coordinate plane below. All right, there it is. All right, which equation describes the function? I'm going to slide down so I can see all my options and my graph there. All right, well, if I want to find out the equation, you could start looking at things to identify, but there's two things I want to focus on, y equals mx plus b, and I'd encourage you to write your own equation first. As we look at this, the pieces we know, I'm going to jump in right away to my y-intercept because I can see it. I know it's going to be something times x minus 4. That means this one's out, this one's out. Okay, now my slope is going to be my change in y over my change in x, and I'm going to pick 2 points that go through the coordinate grid lines so I can easily count my boxes up and over. Now careful, I'm counting my boxes up and over because each box is worth 1 here. So I went up 2 over 3. That's up 2 over 3. The way I write that as a slope is positive is up, so up 2 over 3. I literally write the line over to say what it's over top of, as well as what it's going over. So up 2 over 3 is my slope, and therefore I can identify A as my answer, 2/3 x minus 4. All right, let's take a look at our next question. A student completes math problems at an average rate of two problems every 5 minutes. At this rate, how many math problems does the student complete in 65 minutes? All right, they're giving us a rate like our slope, and so we've got our 2 problems every 5 minutes. And I'd encourage you to write our units here because I'm going to set up a proportion. I'm comparing 2 rates to each other that are supposed to be equal. And that means in my proportion, I must have the same thing on top and bottom of both sides. Notice I set that up before I even brought in our last bit of information here. Now we want to know how many math problems. That means I don't know this value. So I put a variable. The student can complete in 65 minutes. minutes must go on the bottom because my relationship has to be the same, problems over minutes. If I cross multiply here, I see that I get 5x equals 130. And then I can divide by 5 on both sides. All right, when I divide by 5 on both sides, I find that I get 26. X goes into that. And so therefore, we find out that x is 26. All right, he'll do 26 math problems in 65 minutes. An alternate route that I'm going to show you, for those of you that don't like cross multiplication in our proportion here. All right, another way to do it is if this number can go in here. All right, what times 5 is 65? Well, 5 times 13 is 65. And therefore, we would have to multiply 2 by the same amount to get x. Therefore, x would be 2 times 13, which would be 26. It's another way to go about solving proportions. All right, let's take a look at our next question. Sonia is baking cookies. The table below shows the relationship between the number of batches of cookies she bakes and the number of cups of sugar she uses. All right, and there's our table. Based on the relationship in the table, how many more cups of sugar does Sonia use to bake 9 batches of cookies than to bake 3 batches of cookies? I would very much encourage you to cover up your multiple choice answers on ones like this. All right, when you can figure out the problem on your own first, do so. Then check for your answer. All right. In this case here, we're applying our slope. We are recognizing that slope is my change in y over my change in x. And we want to use this information. All right. In this case here, we want to identify what's my change in y first, this being my y value since it's dependent. All right, the number of cups of sugar depends on the number of batches. All right, and if I notice, what does 2 1/4 go up to get to 4 1/2? Well, you can just take your calculator and subtract 4.5 or 4 1/2 minus 2.25, which is 2 1/4. And we see that it is going up 2 1/4 or 2.25, which makes sense in this case because it is going to be a proportional relationship here. And what's it going up here? It's going up by 1. That means that it is going up 2.25 every 1 batch. All right, so we want to now know the next piece of it is how many cups of sugar is it going to take to get to 9 batches? Well, if it's 2.25 cups of sugar per batch, well then 9 batches would be 9 times 2.25, which is going to give me 20.25. That's how many cups of sugar it takes for 9 batches. Be careful, all right? That is one of the options below, but that is not the answer. All right, they wanted to know how many more cups than 3 batches. Well, 3 batches is right here at 6.75, and so I'm going to have to subtract these two from each other. All right, because then I will see that it is 13 1/2 more batches. All right, that's the big thing that they're going to trick you on here. All right, so you've got to be careful. Our answer then comes down. Oops, let me move this down. Our answer comes down to D. Sorry, D is the trick one. Our answer comes down to C, not D. All right, D is the one where they're trying to get you if you read it quickly or looked at your multiple choice answers just before doing the work yourself. All right, let's go to our next question. Carl starts biking at some distance from his house and rides his bike away from his house. The graph below shows the relationship between the amount of time Carl rides and the distance from his house. All right, so here's our graph below. All right, Carl's bike ride. I'm just going to move this up a little bit more there. See if I can get all 4 options. Okay. All right. What distance in miles is Carl from his house when he starts biking? All right, well, we have to understand here in this case what they're looking for. All right, and what they're looking for is for us to understand in a graph the 2 parts. All right, y equals mx plus b is the slope-intercept form of a line, and it gives us 2 key pieces of information. This is my slope, in this case known as my rate, all right, because we do have him traveling somewhere. It's going miles per minute. That's his rate here. And this is my y-intercept, also known as my starting point. And that's the one that we're going to focus on right here because we want to know what distance in miles is Carl from his house when he starts. All right, well, that's my y-intercept right here. All right, so in this point, he is 0.25 miles from his house, and that's it. Next. The scatter plot below shows the cost, y, in dollars of orange trees based on their ages, x, and years. All right, let's take a look. There it is. Okay. All right, now it says, based on the scatter plot, which equation represents the line of best fit for the cost of the orange trees? All right, well, I'm going to take a look at these orange trees here. All right, and I'm going to go ahead and draw my line of best fit. I'm going to move this up just for the sake there so I can see a few things. All right, and for my line of best fit, I like to draw what I call the river, also known as the trend. Do so lightly. This is not an official thing, and it's just something that visually helps me. And if you are ever drawing the line of best fit, this should be erased when you are done. All right, the river is just something that helps me to visualize. I draw the river by outlining the points of the maximum and the minimum. All right, I'm not worried about being straight. I just go right around the points. That helps me, though, to see that my line, all right, as I draw my line here, it should be going through the center of my data. And if I had a ruler, I can't use a ruler on the screen, it'd probably be better than that. All right, a good way to double check my line is that count the number of points above and below. They should be approximately equal. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. All right, right now I see my line is not a good line. All right, I'm going to lower it down just a little bit here. All right, so I'm going to go. All right, try that one. Let's say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I've got like 3 going through it. All right, so maybe that's a little bit better of a line. Now, as I look at this, I want to identify my equation of this line. That's what they're looking for. Again, it's y equals mx plus b. That's on your formula sheet. My slope, I'm just picking out 2 points here that look approximately, it looked like it went about up 10 over 1. So my slope looks like approximately 10. Plus, it appears to be crossing my y-intercept around, I'm going to say 29. All right, now let me identify which one of these equations might match that. All right, if you look at your options, you can see your options. I can't see C and D down here, but I'm just going to scroll down. Pause the video if you want to check out that because I'm going to lose it. All right, but we just said approximately y equals 10x plus 29. And I can see right away B is the only one with an appropriate y-intercept. This one is plus 0, and 40 is way too high. These are way too low. So those ones don't even work. The slope, these two slopes don't work. All right, so it really comes down to B because it's the closest to what I estimated as a 10, and it's closest to a y-intercept of about 30, or I estimated 29. So actually I was pretty close in that one. All right, let's go to the next one. All right, looking at a box and whisker plot here, a teacher measures the time it takes each student in a class to complete a puzzle. The first quartile value of the teacher's data is 4 minutes. The third quartile value is 6 minutes. Which statement must be true? As you can't cover up the answer options in this, but before I go to those answer options, I'm going to write out what they gave me. All right. Now, I know a box and whisker plot looks like this. Now, I'm not drawing a number line. I'm not making this to scale. I'm just giving myself a diagram. All right. And they told me that the first quartile value, known as my lower quartile, is 4 minutes. And then the third quartile value is 6 minutes. We know the median is somewhere in between 4 and 6, but we don't know what it is. And we know the maximum is below 4 or 4 in unique cases. And the minimum is below 4 or 4 in unique cases, and the maximum is above 6 or 6. So which one must be true? That's the tricky thing that we got to come across here. Now let's take a look at our values. About 25% of the students completed the puzzle in 4 minutes or less. Well, I'm going to stop right there. That one is definitely true. All right. Now, I want to be a little bit careful with this. I like that they said they completed it in 4 minutes or less, because we know this section down here is 25%. But let me just draw you a unique situation for a moment. What if I had a box that looks like this? All right, that is not a wrong box where I have 4 and 6. It's not like I'm missing that whisker, but that's if the bottom 25% all did it in 4. The minimum would be 4, as well as the lower quartile, saying that 25% all did it in 4 minutes. But it could also look like this one up here, where we have some that were less than that. So it's in 4 minutes or less. Either of those would be true. But let's go ahead and make sure that the other ones are false and explain why. About 50% of the students completed the puzzle in 6 minutes or more. Well, the 50%, we don't know if that's exactly true or not, all right? Because they completed it in 60% or more. We know that 25% completed it in 6 minutes or more, because 6 is the third quartile. I don't know that 6 is also the median. All right, it could be the median in a unique case, but I do not know that. All right, therefore, it doesn't have to be true. It could be, but doesn't have to be. Exactly 25% of the students completed the puzzle in exactly 4 minutes. I don't know that either. They're trying to trick you thinking 4 represents 25%. But like I said, in this first example here, 25% could have been less than 4 minutes. Only in this example would they have been exactly 4 minutes for the 25%. And then exactly 50% of the students completed the puzzle in 5 minutes or less. I don't know that this median is 5. It could be, but I don't know that. So all these values, B, C, and D, could be true, but their keyword here is must, and that's why they bolded it. So be careful with questions like this. You've got to pick the best answer. Next question. All right, the bar graph below shows the average number of minutes Frank spends each week participating in 4 activities. Based on the information shown in the bar graph, which value is most likely the difference between the number of minutes Frank will spend reading the next 4 weeks and the number of minutes Frank will spend gaming online for the next 4 weeks? All right, now, when you are interpreting graphs, you have to be careful. A lot of the questions are not simply read the graph. All right, it's not going to ask you something straightforward. It's going to ask you to find information on the graph and then do something with that information. So be careful here. All right, the information that they're telling us is that this is each week or 1 week only, but they're asking for us to apply it to 4 weeks. All right, so we've got to be careful with this. All right, and don't look at the multiple choice options yet. Let's figure it out for ourselves. All right, now we wanted to know what is the difference they will spend between reading, which right now is 175, and gaming online, which looks to be, I'm going to estimate about 119. You could estimate 120, but we know it's below 125 and above 100 and closer to 125. All right, now that difference, if I subtract them, 175 minus 119, that difference in 1 week is 56. All right, now we wanted to apply that to 4 weeks. All right, so I need to take that value and take 56 and multiply it by 4. And in this case, we get 224 minutes for our difference. All right, let's look at our options below. Notice they gave you 56 here. This one is a trick. They're trying to get you to do it for 1 week. But again, the key is that this was 4 weeks. And notice 224 is here. Now, if you estimated 120 instead, and you did 175 minus 120, and you got a difference of 55 and multiplied that by 4, you would have gotten 220, and that's close enough to this value. So any estimate of about 125 or so, even if you used 125, you would have ended up with a 200 for your estimate, and still 224 is the closest to that, because they're saying most likely they know you cannot get the exact value of gaming online in minutes because they didn't put it right at one of our exact values. All right, let's take a look at the next question. The Box-and-whisker plot below represents the prices of all cars for sale at a dealership. All right, there's our car prices. Based on the Box-and-whisker plot, which statement about the prices of the cars is most likely true? Again, another most likely. We've got to interpret what they're saying and see if they are true. Always do all of them. Make sure that 3 are not true and 1 is. And we're going for most likely, which means some could be true, but not most likely. All right, we got to go for our most. A, 1/2 of the cars are priced at $12,000. All right, that's not true. All right, it's not 1/2. A Box-and-whisker plot shows us where the half line is, but that means half are priced at less than 12,000 or less, and half are priced at 12,000 or more. All right, so it's not 1/2 are priced at 12,000. So that one is wrong. So it could be all of the cars are priced no lower than $10,000. Well, here's $10,000. 25% of them are at $10,000 or lower. In fact, we know there's at least one car at $6,000. All right, so that is not true either. All right, 1/2 of the cars are priced between $14,000 and $25,000. Well, that is going to be this one right here, 14,000 up here to 25,000. That chunk only represents 25%, so a quarter of the data. All right, not 1/2 of them. So this one is out as well. Let's make sure D is correct. All right, and I'm going to erase my work up here so we can make this one nice and clear as to why it's true. All right, 1/4 of the cars are priced between $12,000 and $14,000. Here's $12,000, here's $14,000. 1/4, in other words, 25% are priced between there, and that is true because each one of these sections on a box and whisker plot does indeed represent 25% of the data. All right, so D is our correct answer there. Next question. The scatter plot below shows the relationship between the time in minutes and the distance in miles that Julie walked on several occasions. All right, thank you for that information. Based on the line of best fit, which is most likely the number of miles Julie would walk in 105 minutes. Now, they've given us a challenge because they did not extend our line of best fit up to 105. This is where we want to look at. All right, so we're tracing it up here, and we notice it is not on our graph, and we see that line's going to keep going. But let's take a look at what the line is doing. Ignore the points right now. They've already given us the line. Notice my line is going through each of these, all right, points right here. That means it's going up 1 over 15. All right, so up 1 over 15. And that pattern continues. All right, well, if that's going to continue, I'm just going to go over there, and over there. So up 1 more, even though it is not on my graph, would indeed be at 7. All right, so most likely they would walk 7 miles in 105 minutes. All right, let's see if that option is down below. And there it is. That is option D. Next question. All right, now we come to our open-ended items. Let's take a look at our first open-ended item here, also known as our constructed response items. Points J and K lie on the same line as shown in the coordinate grid below, our coordinate plane below. All right, thank you for that information. What is the slope of the line passing through points J and K? Show or explain all your work. All right, well, in this case here, I always know that my slope is my change in y over my change in x. On your formula sheet, again, it's shown to you as y2 minus y1 over x2 minus x1. All right, so to find my slope in this case, I would have to plug in my values here or look at them on the graph. All right, it's a little bit challenging because I noticed that I've got a 3.5 and some decimals. I'm going to just use my formula. And I'm going to show my work completely by plugging things in. I wrote down the formula that I'm using. Do that. Copy their formula down first. I'm going to also identify my y values and my x values. I'm going to say that this is x1. All right, this is y1. This is x2. This is y2. In diagrams there, I like to actually put it right on the diagram so I can see it. And now I'm going to take those values and I'm going to plug them in. 5 minus 3.5 over 6 minus 3. And I'm going to do that with my calculator or whatever you want, and I get 1.5 over 3. Now, 1.5 over 3 is not a nice slope. All right, it's got a decimal in it, and I can go ahead and do that division. If you do 1.5 divided by 3, you will go down to 0.5, knowing that my slope is 0.5 or 1/2. Now, on the Keystone exam, all of this work right here, all right, should be inside this box on my video. Obviously, I can't do that because it's not enough room down there. All right, and I wanted you to be able to see it right next to the picture. So as you do that, please make sure you show all that work. Now it says show or explain. I showed all of my work, and I would then answer the question. All right, the slope is 1/2. All right, the slope equals 1/2. If they have a spot for you to put your work, do that. But then I would also explain. I explained to you what I was doing in words. As I did it, I would encourage you to write that explanation down. You can go and look at the answer key to see an explanation that they would accept. But when they say show or explain, I always encourage you to just do both to be safe. All right, let's take a look at the next piece of this. All right, the next piece, continued B. Write the equation of the line passing through the points J and K. Show or explain all your work. I'm going to go back to the previous picture just to continue with that. All right, so we're going to write my equation now so we can see what's going on here. All right, my equation I know is going to start off with y equals mx plus b. As we just found out, my slope is 1/2, but I do not know my y-intercept value. Now you can look at your graph and identify your y-intercept value, which in this case is 2. So therefore my slope is 1/2 x, my y-intercept is positive 2. That's the equation of my line. Now, I've shown that, I've identified. You could explain how you identified 2 on the graph because that's the point where my graph crossed the y-axis. If you wanted to do it a different way, you could plug in one of your values. I'll show that over here. If I know it's y equals 1/2 x plus b, and I know a point like 6, 5, I can temporarily plug that point in. And this is also a good way to just verify that you identified it visually on the graph correctly. I'm sorry, I'm going to actually multiply that. 1/2 times 6 gives me 3. And then I subtract 3 from both sides, giving me 2 as my y-intercept. So that's another way to go about, especially if the point on the graph is not a nice whole number or it doesn't cross through a nice point like this one did. All right, let's take a look at our next question. All right, and the last point of this, points L and M are added to the coordinate plane. The slope of JK is equal to the slope of LM. Describe 2 ways the lines could be related. Again, I'm going back to my graph to go for this one. All right, so you can see this. All right, but you would have to write out your own explanation. But if they have the slope that is the exact same, all right, I'm just going to pick one like this right here and that right there. This would be a line with a slope that is exactly the same. All right, there's one example. Now, slopes that are the same, if 2 lines have the exact same slope, then that means that these 2 lines are parallel. All right, so they asked us what's the relationship between the line JK and LM, the new line. Well, JK and LM could be parallel lines because parallel lines have the same slope. A second explanation is, what if they're not parallel? What if line LM are these points right here? Doesn't that line that I'm drawing right now have the same slope as the line JK? Well, yes, it does. It happens to be the same exact line. And therefore, JK, the line JK, isn't just parallel to LM, it is equal to LM. They are indeed the same line. Those are the 2 different options you have when you know it's the same slope. They're either parallel or they're the same line. Let's take a look at our next question. All right, this is our last open-ended item for Module 2, also known as a constructed response item. Question number 14. Both the box and whisker plot and the histogram shown below represent the heights in inches of the same group of basketball players. So what you see here in our box and whisker plot and the histogram, it represents the exact same. And just a reminder what a histogram is, if you're not familiar with a histogram is like a bar graph, except instead of a single value at the bottom, it's going to have these ranges of values at the bottom. All right, to help you kind of see how many of the basketball players in this case exist in that range. All right, so let's go ahead and take a look at what question A is asking us to find. Based on the 2 data displays, what is the range of the heights? Well, the range of the height is determined from our box and whisker plot. The range is merely asking us to find, it's equal to our maximum value minus our minimum value. Our maximum value and minimum value are shown as the end of the whiskers. In this case, it's 86 minus 72. And that is a range of 14. All right, let's take a look at the next question. B, based on the 2 data displays, what is the interquartile range of the heights? Well, just like the range, the interquartile range can be found here from our box and whisker plot. However, this time the interquartile range is going to be our upper quartile, also known as our 3rd quartile, minus our lower quartile, also known as our 1st quartile. It's the ends of our boxes. The interquartile range is asking how far is this box going to spread. All right, so it goes from 77 all the way up to 83. So I just do 83 minus 77 to get an interquartile range of 6. Let's take a look at C. C and D are the more challenging questions here, all right? And C and D get into the process of using both the histogram and the box and whisker plot. Let's read them. Based on the 2 data displays, how many of the basketball players are 78 inches tall? Based on the 2 data displays, what is the mean or average of the heights? Let's just take a look at these data displays real quick. These data displays do not appear to give us the exact values in our set of data. And that's going to be a challenge because to find the average or the mean, you need to know the exact values. And if we knew the exact values, answering question C, how many of the values are 78, would be very simple. So we are going to use a process of comparing these two graphs, if you will, the box-and-whisker plot and the histogram, in order to get our actual set of data. All right? And I'm going to go through a series of strategies to kind of show what does and does not work. If you need to rewatch this part of the video, do so. Go back and watch it again. All right, but we're going to start off with how many pieces of data do we have. Let's go to our histogram to find that out. Our histogram shows that between 72 and 74, there's 1. Between 75 and 77, there's 1. Between 78 and 80, there are 4 basketball players. Between 81 and 83, there are no basketball players. And between 84 and 86, there are 2. If I add all of those up, I find that we have a total of 8. All right, there's a total of 8 players altogether. Our box and whisker plot takes that total of 8 players and divides it into 4 sections, each of our 4 quartiles, finding that there are 2 players per quartile. All right, that means that there's going to be 2 here, 2 here, 2 here, and 2 here. Now, we know some of this information right off the bat. We know right away, we know our minimum value. Here's 1. So that's one of our 8 pieces of data. All right, and we know our maximum value, 86, is also 1. All right, I have given a space for each of my 8 pieces of data. Now, here's the issue. The median, the lower quartile, and the upper quartile are always found by marking off equal amounts on either side. Given that we have an exact number in each section, because 8 divided by 4 was 2, I have 2 in each section. That means that my lower quartile is not going to be, actually I'm going to use a different color for this, it's not going to be guaranteed to be an actual piece of data in my set. I know it's going to be between these 2 values right here. That's 77. I know my median is going to be between these 2 values right here. That's 78. And I know my, I apologize, putting them in the wrong spot. Let me fix that for you. It's between these 2 values, who's 1, 2, and then 77, 1, 2, and then 78, 1, 2, and then 83. All right? And I know that the numbers on either side are going to contribute to that value, because the numbers on either side are going to say that that value is right in the middle. Now, could the numbers on either side be that number? Why, yes, they could. If they're both that number, then it would work. For example, if this is 77 and this is 77, then my median would be 77. All right? However, if this is 76 and 77 is in the middle, then this has to be 78. All right, so that's just the understanding of how we find our lower quartile and upper quartile. Now let's explore the options that we know. We know at this point that if there's one value of 72, that's this one value right here. All right, that one is 72, okay, because that's my minimum. That means that the other value in this lower set is not 73, it's not 74. It has to be between 75 and 77. So if that's the case, let's just understand a little bit about that. We got one value there between 77, and let's just test a value. I'm going to put it in green. I'm going to test the first possible one of 75. If I think that one value is 75, and I have a median of 77, that means that the other value on the other side has to be 79 in order to have a lower quartile of 77. Is 79 possible? Well, if I look, 79 is here. That is in my third quartile. this section. So it is not possible for this one to be 79. If it was 79, then it would be too high. So therefore, if this cannot be 79, this cannot be 75. I'm also going to test the next one of 77. You'll understand why I'm jumping up to 77. It's because 76 is the right answer. All right? But if I say that's 77, then this has to be 77. 77, all right, being right here, all right, shows that, hey, both of them could. However, there is only one piece of data that exists between 75 and 77. If both of these are 77, that would be two pieces of data. And therefore, this number cannot be 77. And that is why we must conclude at this point that this number has to be 76. This one value right here has to be 76. And therefore, this one has to be 78. All right, it has to be 78. And if this one is 78, and we're going in order, then there are two values, all right? There are two values that we see here that lie between 77 and 78 that are either 77 and 78, and therefore this one must also be 78. All right, so I know I've got 78 in here, 78 in here. And if that one's 78 and I have a median of 78, then this one must also be 78. All right, all of those must be 78, giving us at least 3 78s so far. And if that's the case, now I need to go to my upper quartile to see if I could have another 78. If I have 78 in here, which is possible, you know, I mean, it could be anything between 78 and 80. All right, and here I see it could be between 78 and 80. These two values between 78 and 80 are able to exist in there. All right, but if it's between 78 and 80 and I make it 78, then my upper quartile of 83, when I have a maximum of 86, is not possible. All right, in order for the upper quartile to be 83, if I had a value of 78 there, I would need my top value to actually, my very next value to be 88, which doesn't work in this case. All right, so I know that that's not possible to have it be 78. What about it be 79? All right, if it's 79, then I would need this one up here to be 87 in order to come to the middle on 83. Once again, that's too high. That's beyond my maximum, and so 79 is not possible. So therefore, this value must be 80 because I needed one more piece of data that existed in the 78 to 80 range because there are no values of 81, 82, and 83. So this has to be 80. And if that's 80, well then what value on the opposite side of that would get me to a median of 83? Well, I know that 80 plus some number divided by 2 gives me a middle of 83. So if I go backwards, I can figure out what that is. You could guess some numbers if you want, but if I go backwards, I see that 80 plus x is going to equal 166. And if I subtract 80 from each side, that's an 8. If I subtract 80 from each side, I find out that x is equal to 86, making this value 86, which is possible because it's not beyond my maximum, and I have two values in the 84 to 86 range, in which case both here are 86. Those are my data sets, and now with this piece of data, we can go back and answer C. In C, how many pieces of data were 78? 3 players. All right, 3 players had a height of 78 inches. Sorry, I said plays. 3 players had a height of 78 inches. And now D, you can use these values to find our mean or our average. Remember, our mean, otherwise known as our average, is always the sum of all the players divided by the number of players, how many there are. So in this case here, you can add up all of my values. All right, get out your calculator and go ahead and add them all up. And if you add it all up, you should get a total sum of 634. And we're dividing by 8 total players, giving me a mean of 79.25. All right, 79.25. Now, if you had trouble discovering C, because that is the more challenging piece here, and you didn't know the exact numbers, I would still pretend as though you do. Go through, give your min and max, and give the values that make sense to you and put those down so that in D they can see your work is adding up all the values, the 8 values in the data set that you found, and dividing by 8. They could give you a carry-through error at that point because they're looking to see if you actually know how to take the average or the mean of a set of data.